From radio waves that are meters long to X rays that can penetrate our body, telescopes allow us to see things in outer space that we can't see with the naked eye. In Chapter 2, we're going to talk about the electromagnetic spectrum. So, electromagnetic radiation, or EMR, is a wave with a changing electric and magnetic field that are perpendicular to each other. So, one goes, in essence, north south, the other one travels east west. And electromagnetic radiation includes all of the energy that we receive from the sun. And these waves are able to transmit energy from one location to another through vibrations. So the fields vibrate and then the energy is transferred through space. Now, the shortest wavelengths are gamma rays, and the longest wavelengths are X rays, which could be hundreds of kilometers long. And in the middle is our visible light at 0.5 times 10 to the negative 6 meters long. Okay. We also have microwaves, ultraviolet waves, and X-rays. So transverse waves mean that vibrations are perpendicular to the motion of the wave. So transverse waves are going to be like waves on the ocean where they move up and down while going this way through space. Now, longitudinal waves are going to be vibrations in the same direction of motion. So if you're like shoving back and forth on a spring. When we talk about transverse waves, the crest is the highest point on the wave and the trough is going to be the lowest point on the wave. A cycle is one complete vibration of one crest and one trough. Wavelength is going to be the length of the cycle, and the frequency is the number of cycles per second, and we measure that in hertz. So here's an example of a longitudinal wave. Like I said, it looks like you're compressing a slinky, and a transverse wave that will go up and down will travel forward through a location, similar to how waves look on the water. So the universal wave equation is velocity equals wavelength times frequency. And for all types of electromagnetic radiation waves, the speed is always the speed of light at c equals 3.00 times 10 to the power of 8 meters per second. So sometimes you'll see formulas with V, occasionally you'll see formulas with C. And again, this is in your data booklet as well as the speed of light. So velocity is speed in meters per second. Lambda is wavelength in meters, and frequency is represented in hertz. So an excited atom from a neon sign emits electromagnetic radiation with a wavelength of 6.4 times 10 to the 7 meters. We're going to calculate the frequency. So my formula started off as V equals lambda times frequency. We're going to calculate frequency. So we're ending up with velocity divided by lambda. So that's its wavelength. So we're going to go 3.00 times 10 to the 8th meters per second divided by 6.4 times 10 to the negative 7th meters gives us a total frequency of 4.7 times 10 to the 14 hertz. So that's how often waves happen in each second. Now, if the sign is 25 meters away from an individual, how long is it going to take for the light to reach them? So remembering back to our kinematics in Science 20, we have velocity is equal to distance over time. And so therefore time is equal to distance divided by velocity. So our distance is 25 meters. Our speed is 3.00 times 10 to the 8th meters per second. So we're going to get a total time of 8.3 times 10 to the negative 8 seconds. So incredibly, incredibly less than a second for that light to get to that person 25 meters away. So the complete range of electromagnetic radiation can be arranged using both wavelength and frequency. And we can classify different types using the nature of the source, the energy transmitted, and its effect on living tissue. So radio waves have the lowest frequency and therefore the highest wavelength, because again, everything must balance out. So if a frequency goes down, wavelength must go up. So this is produced by electrons vibrating in circuits, and it's used for telecommunications. And radio waves cannot penetrate metal, which is why they make good antennas. So it won't enter that metal antenna, but it will make it vibrate, and then our radio will pick up that sound. We could have ELF, which is emitted from circuits at 60 hertz. And waves with a wavelength of 4 meters are used for MRIs. And they don't harm the body because the body's tissue because there's such low energy levels. So microwaves are used for radar with a higher frequency, satellites, as well as cooking food, which is going to be a slightly lower frequency. So like 2.5 gigahertz. Now, they transmit more energy than radio waves. And because living tissue has a high percentage of water, microwaves can harm tissues, especially the eye lenses, because of the large amounts of water in those tissues. Causes it to heat up. So infrared radiation causes molecules to vibrate, which produces heat. So our bodies produce also infrared radiation. And waves with a frequency of about 4.3 times 10 to the 11 hertz. So skin sensors can detect infrared radiation using heat receptors because the energy of infrared can't be seen, it can only be felt. We also use infrared radiation to beam information to devices, like with a Wii receiver or a television remote. So visible light is the complete range of all the colors that can be seen by the eye. So red, orange, yellow, green, blue, indigo, and violet. So the limits are violet at a wavelength of 400 nanometers and red at an upper wavelength of 700 nanometers. And visible light is typically emitted by things that are hot. So remember, light is not specifically a wave, but a photon and a packet of energy. And the higher the wavelength, the lower the energy. So again, when we looked at radio waves with a large wavelength, they have very low energy. So red has a lower energy than purple would when we're talking about visible light. And visible light is important for life on Earth because plants use the photons and absorb energy from visible light in order to grow. So that photon is going to be absorbed by chlorophyll, and then the energy produced is going to be used to convert carbon dioxide to water and sugar. Ultraviolet radiation is emitted by very hot objects and has a frequency of 1 times 10 to the 18 hertz. So it has a very high frequency. Photons have more energy than visible light, and this light can cause cancer and premature aging, so wrinkles if you're out in the sun unprotected for long periods of time over many years. Ultraviolet radiation can be divided into 3 different types, UVA and UVB, which have a high energy, and we need to protect our eyes using sunglasses. And UVC is primarily absorbed by the ozone layer up in the stratosphere, but it can cause DNA mutations that can lead to cell death. So we really need to protect our skin from UVC. X-rays are very high energy waves again, and they're created when electrons strike metal, and they're produced using a high voltage tube. X-rays are able to penetrate our skin, but are absorbed into our bones, so it provides a dark and light image. So this is a powerful form of ionizing radiation, which can cause significant DNA mutations. So it's important to keep the exposure to radiation as short as possible, and this is why they have you wear a lead vest at the dentist and avoid X-rays if you are pregnant. So last is gamma radiation, and this is the highest energy radiation and the shortest wavelength. So all gamma radiation is radioactive photons from radioactive decay, and it can cause DNA mutations very quickly. So it's the most harmful form of radiation that's emitted by the sun. So that's our lesson today on electromagnetic radiation. I hope you enjoyed it.